Nitrogen and hydrogen can be combined in the Haber process to make ammonia, but ammonia will also naturally break down into nitrogen and hydrogen. This is called a reversible reaction, and we can write it a little bit more elegantly in a single line. We use this symbol made up of two arrows to represent both reactions, the forward reaction and the reverse reaction. I'm going to use the salad drawers from my fridge to represent a reversible reaction and the reactants in products. Starting with all reactants, I'll use this glass to represent the forward reaction, which is quite fast because we've got lots of reactants. The reverse reaction is going to be really slow because I've not got very many products at the moment. In real life, both of these processes will happen at the same time, the forward and the reverse reaction. Gradually, the forward reaction will slow down as we run out of reactants, and the reverse reaction will speed up because we have more products. Eventually, we'll notice that the level of reactants and the level of products doesn't change. The rate of the forward reaction and reverse reaction is the same, and we call this dynamic equilibrium. I'll use my kitchen version of a measuring cylinder just to double check this, and we can find that the forward reaction has got about 100 mils, and the reverse reaction has got the same volume as well, just to confirm that we are at dynamic equilibrium. An important property of a reversible reaction is if the conditions are kept the same, we will always reach the same equilibrium point, regardless of our starting point. To demonstrate this, I'm going to start with all products this time. The reverse reaction starts off quickly and the forward reaction starts off slowly, but over time they will eventually reach the same rate, and we have once again reached our dynamic equilibrium. So reversible reactions present an important question. If I have a particular reversible reaction with reactants and products, when I reach that dynamic equilibrium, am I going to have lots of reactants and a few products, roughly an equal number of reactants and products, or am I going to have lots of products and very few reactants? The answer to this question lies in a figure called the equilibrium constant, which is represented by a lowercase k. For a general reaction, with reactants A and B combining to make products C and D, balanced with lowercase letters, we can calculate the equilibrium constant K with the following equation. The square brackets just represent the concentration of whatever's inside those brackets. Products of the forward reaction always go on the top and reactants go on the bottom. Back to our earlier question, if we have a small equilibrium constant, we'll have lots of reactants and very few products. But if we have a big equilibrium constant, the equilibrium point will lie to the right and we'll have lots of products and very few reactants. You're probably familiar with a common reversible reaction, that is the dissociation of water into H plus and OH minus ions. The equilibrium constant for this reaction is 1 times 10 to the negative 14. Which means that we've got lots of water and relatively very few ions. Equilibriums such as this are sometimes represented with a slightly different arrow to represent where the equilibrium point lies. Equilibrium constants also do not have units. Never ever. It's just a ratio. Think about our original reversible reaction, nitrogen and hydrogen combining to make ammonia. What do you think the equation is going to be? Well, we always put products on the top and reactants on the bottom, and also include the balanced moles as powers of each chemical. As always, there are special cases. When working with gases, we can use either concentration or pressure to work out our equilibrium constant. For liquids and solids, we take the concentration to be 1. The most common of these will be water. Here's an example. Dissolved ammonia reacts with water to make an ammonium ion and an OH minus ion, which is why it's alkali. The equation is nicely balanced, so we can work out our equilibrium constant, putting products on the top and reactants on the bottom, not including water, because that's just one. One more example, I promise. I want to look at an equilibrium with some solids in it. Remember that these are equal to 1. Calcium carbonate can be reduced to produce carbon dioxide gas, but this gas is the only non-solid thing in the reaction, so the equilibrium constant is simply the concentration or pressure of carbon dioxide.